So this is the part in the course where I usually talk about infectious disease models, and it seems particularly relevant to all of us at this point, given that we're in the midst of a global pandemic. So as a result, we're going to spend a little more time than I usually would on this subject, but I hope that we'll walk away with it with a better understanding of what's actually going on right now. So to start, let's actually look at the data on the coronavirus outbreak in the US, and we'll try to figure out how we can build a model from here. So there are many websites tracking this information. The data that I'm showing comes from a particular website linked to in the Excel spreadsheet that you see on screen. And I've got two columns that I'm going to focus on: the day number starting from February 15th, and then the number of cases in the US. You could also do something like this for deaths, but I'm going to focus on cases for the moment. All right, and the first thing you usually want to do to build a model is to actually look at the data. And so let's do that. I'm going to highlight these two columns. And by the way, you could easily do this in Octave or Python or any data analysis tool. I'll stick with Excel for now just because it's relatively easy to get off the ground. And so we'll insert a chart here. I'd like a scatter plot. And you'll notice here the x-axis is the day number and the y-axis is the number of cases. Now, this looks like the epidemic is definitely accelerating, right? It's getting steeper and steeper as time goes on. But because it's a curve, it can be very difficult for us to, at least in the current representation, tell exactly what type of function is appropriate for this type of trend. And so what we've done previously is we've used logarithmic transformations to tell whether we have a power law, whether we have logarithmic growth, whether we have exponential growth, or linear growth. And so we can do that here by clicking on our axis. And I'm going to just click on Format Axis for the Y and switch to a logarithmic scale. And you'll notice that when we do that, we see that at least starting after about 15 days, it looks like we have a very, very linear trend. And again, this is the x-axis is normal, the y-axis is logarithmic, and so that suggests that this is a scenario where after day 15, we've got exponential growth. And so I'm actually going to change the data really quickly. I'm just going to remove, oops, let's go back there. I'm going to remove the first 15 days worth of data here. And now we can focus in on the data where it seems like the pattern has really emerged. And that looks like we had somewhere between 10 and 100 cases when this really started to grow exponentially. And we can even add a nice trend line to this. And in this case, we'll add an exponential function. And if you do that, you can see in the background here, we can make that a little bit, let's make it solid. And maybe we'll make it red so it's a little easier to see. You can see, wow, that's a really, really good fit for the pattern that we're seeing. And if we want to look at it a little further, we can even look at things like the equation and the r squared value. And you see we have an r squared value of 0.999. So this is like the classic example of exponential growth going on right here. And what I think is a little bit scary about this is that this type of function grows really, really, really fast. So let me actually do some calculations here. So the fit that we found is 0.921 e to the 0.2896x. So I'll type that in here. And exp is for the exponential function, 2896 times. And then I'm just going to click in another cell here. And so what we can do now is we can fill in a day number and see, based on this trend, how many cases are there going to be in the future. So currently, we're on day 37. So if I plug in a 37 here, it says that we would be expected to have 41,000 cases. And so it looks like the last data point was a little bit higher than expected. If we go another 10 days into the future, it's predicting that we're going to have 750,000 cases. And if you go another 10 days beyond that, now we're looking at 13.5 million cases. And as you can see, this is not good news. Let's hope that trend doesn't actually hold. Let's go another 10 days. And now it says we have 2.46 times 10 to the 8th. That's 246 million cases. So that's about, I think about 70% of the US population. And if you were to continue, now we have more people infected with coronavirus than we have people in the US, which is not actually possible because this is only US data we're looking at. So a couple of things to notice here. One, fitting an exponential curve to this data works really well. It also gives us some predictions that are a little bit concerning in terms of where we could be headed in the not so distant future if this pattern were to continue. The pattern is an incredibly good match for an exponential function. But on the other hand, this can't possibly continue indefinitely because we don't have an infinite number of people. And so one of the hazards of using just a purely data-driven model where we've fit the model to the data is that it doesn't explain why things are happening the way they are. It just explains what is happening, right? And when we try to make predictions based on the past trends into the future, you can end up with rather absurd predictions. So as an example, let me just show you a quick comic that illustrates the absurdity of this idea. So this is what's called extrapolation. Extrapolation is taking the current trend and projecting it into the future. And so here, one of my favorite comic strips, they say, well, yesterday you had 0 spouses, today you have 1. So if the current trend, by late next month, you'll have over 4 dozen husbands. Well, obviously that's ridiculous, right? You can't just assume that because we had a linear trend over the last 2 days means we're going to have a linear trend indefinitely. And the same thing would apply here. Just because we've had an exponential trend over the first 37 days of our outbreak, we cannot assume that we're going to have an exponential trend indefinitely. But a data-driven model doesn't really show us that, and it doesn't allow us to explain why we have an exponential trend either. And so if we want to actually understand infectious disease, we're going to need to build what's I would describe as a mechanistic model, a model that accounts for the mechanisms that give rise to the growth rather than just trying to describe the growth itself. All right, so let me shift gears for just a moment. Let's take a look at the data from not coronavirus, but from another outbreak. In fact, this is actually just the seasonal flu from the state of Pennsylvania a few years back. And you see that when you plot the number of cases by week, so this is not by day, this is by week, you do see that it does look like there is a period where there's exponential growth, but eventually that exponential growth is going to peak, and then it's going to decay, perhaps exponentially as well. It may be symmetric, it may not. This looks a little bit asymmetric. And you notice that based on the data we have for coronavirus, there's no way that we could forecast that type of behavior. But the claim is that if we understand the mechanisms that give rise to the spread of disease, then we could actually do that. All right,